So 2, 3b. Whoa, that's thick.
Oh, yeah, no homework has done.
2, 3b. Oh, were they all together?
Yeah, it was 2, 3b is 31, 33, 34.
Oh, you did those. Okay, so now you'll be able to do them, though.
But now
If you did them already. Yes. Okay. We're going to do some more continuity. Whoa, they fixed it. Yay, that's so good. What? They called it pen lagging. And it did. It was bad, yeah. Yeah, it was bad. Okay, here we go. We're going to do, first part, we're going to do a little intro. They call it an exploration problem in the book. Okay, so we're going to let f of x equal x cubed minus 7x minus 6 over x squared minus 9. Okay, letter A. First thing we're going to do is we want to find the domain of this function. First, find the domain. Hopefully, you're pretty solid on that by now. We've done that so much, like in ham and here at the beginning. So the domain would be what? All reals except plus or minus 3. All reals except for plus or minus 3. You can factor the denominator if you want to. Okay, so something's going on at 3 and at negative 3. So let's go ahead and go to our calculator and let's graph this function. When you graph this function in y1, don't forget parentheses around the numerator and the denominator. So we graphed it on our calculator. We look at the graph and it looks like this and this. Okay, but we know that plus and minus 3 are not in our domain. So at negative 3, there's an asymptote. There's a vertical asymptote at x equals negative 3. Okay, and then if you go over to positive 3, if you actually hit trace on your graph and you go to positive 3 on your calculator, there will be nothing at the y there, nothing. Okay, it's not in our domain. So over here at 3, there's going to be a big old hole in the graph. You can't really see it though. You know, I wish that the calculator put a hole, like a circle around it, but they don't. But you know that that's a hole in the graph. So at x equals 3, we have a hole. All right, so knowing those things, the next question they're going to ask you is going to be what types of discontinuity happen and where? Types of discontinuity. Continuity. I hope I spelled that right. All right, so we know where they're happening. We know the points of discontinuity are at x equals negative 3 and x equals positive 3. So what's it called at negative 3 when you have an asymptote like that? What type of discontinuity is that? Infinite. Perfect. Yes. Anytime you have an asymptote, as you're going towards 3 from the plus and minus, or negative 3 in this case, you're going off to infinity. Your y's are going off to infinity. So it's an infinite discontinuity. At 3, what's that called? Starts with an R, not an H. Removable. I know you want to say hole because it is a hole in the graph, but it's called a removable discontinuity. Someone removed that point out of there. I will. I'm going to mark you off just because you asked. Okay, now part C. Let's go ahead and find the limit as x approaches 3 for this function. So yes, we still need to know how to do limits. This is part of this chapter. Find the limit of this function as x approaches 3. Now, I have it graphed here. Okay. I can hit trace. And I can plug in 3, and I don't get a value. And I can plug in 3.0001. And I get that y is 3.333333. Okay? And I can plug in 2.9999999. Y is 3.3 repeating. Oops, oops. All right. Okay, so the limit would be 3 1/3. It's kind of hard to see that way. If we actually wanted to do this algebraically, do you know what we would have to do? A lot. Yeah. Okay, do you see how x cubed minus 7x minus 6 and x squared minus 9? X minus 3 is a factor of both of those. So if you were to try and do this one algebraically, which you might be required to do like in college or something, but I won't, I'll let you use your calculator here. But you would have to do probably synthetic division with 3 into here, and then factor it out, and then reduce your factors. You know what I mean? Or no? Like, the bottom you can factor. X plus 3, x minus 3. Oops, minus 3. I know that x minus 3 is going to be a factor of the numerator because that's how a whole is made. But how do I get that out of here? I can't factor this. So what you would do is you would take 3 and you would do synthetic division and get it down to a quadratic.
Why not -3?
At -3, that's the asymptote.
Oh.
Yeah. But it's okay. You can graph it. That's fine. Now, here's the question that they asked you in your homework last night that was very confusing. What should y equal to make it continuous?
Wait, wouldn't the top be x plus this? That's just the removable
No,
whole?
no, because the removable whole is at x equals 3, so the factor that goes with that is x minus 3. Yeah. Okay, so what should y equal if we want to make it continuous? If we want to make it continuous at x equals 3. Okay. So what should we let y equal? Like, let's say we want to go ahead and make it continuous there. We can't make it continuous at the infinite one. You just can't. Yes, we would let y equal 3 1/3 because then it would be continuous there. See, remember the limit has to equal whatever the value is. There is a limit there. There's no value there, but if we make it the value, then it's continuous all of a sudden. All right, now the next part, part B, is the part that my dad and I spent many a times arguing about, and he was right. Okay, here we go. Continuous on an interval. Continuous on an interval. So what we have here is basically you have a continuous function. Here's the definition of what a continuous function is. And this is where we disagreed a lot. It's continuous at every point of its domain. A continuous function is continuous at every point of its domain. Okay? So you could pretty much argue that anything is continuous that we've been doing so far. And we say that it's not continuous at some points, but if they're not in the domain, then it's a continuous function anyways. I don't know. It paused?
No,
It's okay? No, it's so...
It's just saying that she can't push it.
Okay. So, like, for example, here we go. Number 2. Number 2. The question that they're going to ask you, or they're not even going to ask you a question, they're going to say, explain why the function is continuous. And you're going to look at it and say, but it's not. Explain why, yeah, f of x is continuous. And I would sit there and I would argue with my dad and say, it's not continuous. And then he'd say, well, let's go back to the definition. And he was right. So f of x is 1 over x. This is still number 2. So we're going to explain why f of x is continuous. Well, I look at that and I'm like, that's not a continuous function. At x equals 0, there's a problem. There's an infinite discontinuity. But take a look at what they say a continuous function is. A continuous function is continuous at every point of its domain. Is 0 in the domain of that function? No. So the domain of this function is all reals except for 0. So is this a continuous function? Yep, it is. It's continuous because it's continuous at all the points in its domain. 0 is not in its domain, so I can't even talk about that. Isn't that weird? The book goes into it. It's weird.
But why do we know that?
Because they ask you for that. They say, explain why the given function is continuous. And you say, because it's continuous at every point in its domain. That's really all you have to say.
So it would only be continuous if it's infinite.
No,
This is like a whole removable.
like a removable, yeah.
That wouldn't be continuous. Because the whole is.
Right, and you could have a dot, and that's in its domain still, but yeah. Or a piecewise function. Piecewise functions don't really go with this either. But any of these rational functions, like f of x equals 3 over x minus 4. Explain why that's a continuous function. Because that would be continuous everywhere in its domain. That graph is all smooth except at 4. Yeah. Yep. Okay, and then we're going to do the last part, which I assigned problems to, and you were really confused about this one. And this is all about composites. Okay, you're going to get some crazy looking functions, and you're not allowed to graph them, but you have to tell whether or not they are continuous. Okay, so here's, there's two theorems. There's Theorem 6 and Theorem 7.
Where's 1, 2, 3, 4, 5?
Oh, they're somewhere. We've done them. We just didn't call them that. All right. It says here that these combinations, it says f and g are both continuous functions. Okay? F and g are both continuous separately. F is continuous, g is continuous. Okay? Then that means that f plus g is also continuous. F minus g is also continuous. Okay, this is a theorem. F times g is continuous, and f divided by g is also continuous, provided that this function g doesn't equal 0. And a constant times either of the function, these are all continuous. Okay, you don't have to prove that, you just have to know it. I think I had to prove that in college. It was horrible. Really bad. Okay, so given f, given g, those functions are continuous, and then that means that the sum, difference, quotient, product, even a constant, all of those are also continuous too. Okay, Theorem 7 says, so not only are the sums and all that continuous, but it also says that the composites are continuous. F of g and g of f. Those are both continuous also. So functions within functions are continuous. And they do a really good job of like describing it, and I have this whole picture thing, but we don't need to do that. Okay, so let's look at the last one. So you had some of these in your homework, and they were probably really confusing. They're really not that bad. So number 3 will say something like this. Show that, or explain, you're not allowed to graph this, okay? Show that y equals the absolute value of x sine x over x squared plus 2 is continuous. Okay? Show that, or explain. Explain why that's continuous. They'll tell you it's continuous, or maybe not. They'll say, is it continuous, yes or no? And you have to say why. So first of all, let's start with, there's an outer function and there's an inner function. The outer function is y equals the absolute value of x. Is the absolute value of x, is that a continuous function? It's that V shape, okay? So the absolute value of x is continuous. All right. So that is like composition of functions. This function inside is being composed from the outside. So now we have to look at y equals x sine x over x squared plus 2. Okay, and we can break this down into 3 different graphs. We can break this down into y equals x, y equals sine x, and y equals x squared plus 2. So this is being multiplied to this one, and then you also have the parabola on the bottom.
So since all 3 of them are continuous,
Mm-hmm. Yep, exactly. So this is just a line that's continuous. This is the sine wave that's continuous, and this is a parabola that's continuous. So since the composition of this thing inside of the absolute value and all of them inside of there were all continuous, then the entire thing is continuous.
So all you have to do is just write this up.
Yeah, you have to like write each one separately and say why those each ones are continuous, because they're going to be things you know. You know the line y equals x. You know sine x, you know parabolas, and you know absolute values. Those are all continuous functions, and so the entire thing would be continuous.
So all we have to just do is like write that y.
Yeah, just like this kind of thing right here. Yeah, you could even do like pictures, like I said. Look at that. That really looks like a sine wave, doesn't it? No.